All right, I think you are really going to like 3.2 because it's a lot of review stuff. It's a lot of things that we've already gone over from chapter 2. We're going to be graphing functions. Remember that we are focusing on transformations of functions this semester, on that concept of understanding the shape of the function and what the equation does to that parent function. So I want you to stop and review, name the parent functions. You've got your graph. None of them have arrows on the ends. That is my nemesis here. So throw in your arrows to show that these are continuous graphs. They don't stop, except for this one does stop right there at the origin, but everything else continues forever in both directions. These are 1, 2, 3, 4, 5, 6, 7 parent functions that we are focusing on as we're doing these polynomial functions. Pause the video, name each of these, and then come back to see how you did. This first one, we have the constant function. It's linear. These first two are both linear, but we're going to call this one specifically the constant function. My constant function has a slope of 0. It's my horizontal line. My parent linear function, the one that we call the parent linear function, is this function y equals x. Positive slope of 1 through the origin. Then we move on and we've got our absolute value function. F of x or y, I'm going to go ahead and do function notation. F of x equals absolute value of x. We have our quadratic function. Parent function f of x equals x squared. We have our cubic function. F of x equals x cubed. And then we've got those two inverses. Our inverse of our quadratic function is our square root function. And remember, we have limited it so that we only show half the parabola so that it's actually a function. F of x equals the positive values square root of x instead of negative square root x. And then the inverse of our cubic function is the cube root function. F of x equals cube root x, and we get the entire graph. A function and its inverse are reflected across this line y equals x. I'm going to go ahead and sketch in that line of reflection. If I reflect my parabola across that line, I get the inverse. This one, again, reflected across that line. We would take our original cubic function and reflect it across that line to get the inverse. All right. If you had already put away your parent function page, this is another good place to look back at those parent functions as we're graphing using transformations. We've got an application problem thrown in here because this is business college algebra and the whole purpose is to be able to apply this stuff. So here we go. The graph shows iPhone sales in millions of units, and you can see that we're looking at the years from 2011 to 2015. Millions of iPhones sold, obviously increasing as the market improves. It asks us to estimate and interpret the function value for f of 2013. Well, at 2013, it doesn't look like we really have to estimate. It looks like we can say in 2013, there were 150 million iPhones sold. If you just tell me 150, that is not right. 150 is not the same thing as 150 million. So make sure that you read the information given to you on your graphs. What is the domain that is shown? Well, domain is the set of x values, and as I look at this graph, my domain includes the years from 2011 through 2015, square brackets, because those years are on the graph. Estimate the range shown on the graph. My range is my set of y values. So if I'm looking at the range on the graph, I'm looking at these y values that are included. So it looks like that's right in the middle. Let's say 75 up to 225, and those are in millions. And that is an estimate. All right. Review graphing our linear functions. Slope of a line. That equation, m equals change in y over change in x. We also talked about slope as rise over run. Or the more formal definition of slope, y sub 2 minus y sub 1 over x sub 2 minus x sub 1. The slope-intercept form of the graph, that is my most used function form of the linear function. It's my go-to. It's where I am headed typically when I'm working with a linear function, y equals mx plus b, where m is my slope and b represents the y-intercept, because if I plug in 0 for x, this term goes to 0 and I'm left with b. So my y-intercept is 0, b, whatever that value is given as. And the point slope form is the form I can use when I don't have all the information I need for my slope-intercept form. As long as I have any point on the line, it works with any point on the line. So my point slope form is y minus y sub 1 equals m times the quantity x minus x sub 1, where we have a given point that we plug in, x sub 1, y sub 1, and we take those values and plug in there. All right, graphing linear functions. Grab your straight edge. These two are given to us in slope-intercept form, so that's handy. We don't have to do any work there. We can say, okay, for this one, my slope is 2/3, and my y-intercept is going to be 0, 1, my y-intercept. So what does that mean to me on my graph? Well, I've got a positive slope, so my function is going to be increasing as I move from left to right. I'll go through the y-axis at 1, and then from that point, 0, 1, I will apply the slope. Rise over run. So I go up 2 over 3, up 2 over 3. When I've got an increasing slope, I go up and to the right. Or you know what I could also do? I could do the opposite of that. I could go down 2 and to the left 3. Either way allows me to end up with a line with a positive slope. I only need 2 points to graph a line. There we go. So this point came out to be 1, 2, 3, 1, 2, 3. So 3, 3 up, if I go up there. This one would be a -3 down 1, so -3, -1. -3, negative, yeah, -3, -1. -3, -1, because we're going down 2. All right, what about this one? Well, I see that I've got a negative slope here. Let's change colors. Negative slope, -3/4. My y-intercept, where x is 0, y is going to be -2. That y-intercept is my starting place. So I start on the y-axis at 0, -2. I've got a negative slope, so I'm going down. So when I graph my next point, I can go down and to the right, or I could go up and to the left. I want that decreasing line because I've got a negative slope. Whichever way I choose to go, my rise up or down, 1, 2, 3, the run is 4, 1, 2, 3, 4, that would be a point on my line. Or I could go 1, 2, 3 up and 1, 2, 3, 4 back to the left. And that gives me a line with a negative slope. All right. We graph those two from our slope-intercept form of the equation. When we look at the next page, we don't have the slope-intercept form of this next line. So we've got some choices we can make. First choice would be to solve my equation for y and put it in slope-intercept form. Second choice would be to find x and y intercepts. Plug in 0 for y, that one's not going to work nicely, right? If I plug in 0 for y, negative 10 divided by 8 is not pretty. But if I plug in 0 for x, I can get my y-intercept pretty nicely there. That's going to be a nice number, nice integer value. But let's go ahead and let's just put it in slope-intercept form, and we'll choose to solve for y to get it in slope-intercept form. If we choose to solve for y, we're going to subtract 8x from both sides. So that gives me negative 2y equals negative 8x minus 10. Now I'm going for slope-intercept form. Y equals mx plus b. So this is the order I want, definitely over here on the right side of my equation. Negative 8, however, is not my slope. I haven't finished solving for y. I need to divide each term by a negative 2. And you might want to write that negative 2 below each term, because sometimes people will divide the first term and then forget to divide the constant. A negative divided by a negative is a positive, so that's a positive y. Negative divided by negative is a positive, so I have a positive slope 4x plus 5. That's the equation of my line in slope-intercept form. This is my standard or general form. This is my slope-intercept form. And it allows me to say, okay, my slope is a positive 4. My y-intercept is 0, 5. If I plug in 0 for x, I'm left with 5. That's my starting place right there. My slope is 4. So my rise is 4. What's my run? Well, 4 is the same thing as 4 over 1, right? So I'm going to go up 4 over 1. If I go up 4, I'm off of my graph, so that's a little messy. Let's go down 4. 1, 2, 3, 4. Which way do I go, left or right? Well, I need a positive slope, so I'm going to move this point back off 1 to the left in order to make sure that my line has that positive slope. 4 is a really steep slope, so I have a line that is a very steep line. It started at the point 0, 5, and then I ended up at negative 1, 1 for that second point that I put on my graph. Oh, you know what? We were supposed to do domain and range for all of these. My instructions said identify domain and range of each. Every line that is not a horizontal or vertical line has domain and range, all real numbers. Domain and range are all real numbers, negative infinity to positive infinity. And that's the case over here for both of these as well. Oh, for both of these, I'm getting ahead of myself. Let's graph the next one before we make an assumption. This one has a domain and a range that are both all real numbers. What about this one? Y equals 3. What do I do with that? Well, y equals 3. Y is 3 here, right? Is that the only place y is 3? Well, no, y is 3 over here, and over here, and over here, and over here. So y is 3 is actually a horizontal line where y is 3. Now y is 3 for every x value. This is my constant function. My slope is 0. My domain is all real numbers. But my range is just that single value 3. So when I write my range, I use fancy brackets, fancy braces, and put the 3 inside because it's just a single value, not an integral. All right, great. Transformations, graphing with transformations using our parent functions. So we're identifying the transformations. Now notice I've been told to do several things. Graph each function with its parent on the same set of axes. So you know what? We are going to start right there with parent functions. Parent function. For this, I've got a square root function. And we know from our first page, there's my parent function. So I'm going to go ahead and say right there, y equals square root x. That's my parent. What about this one? Well, I've got absolute value bars. That's an absolute value parent function centered at the origin. V shape going up. That is y equals absolute value x. There's my parent function. Down here, I've got an x squared, that's quadratic. My quadratic parent function is that parabola that opens just so, centered on the origin going up, y equals x squared. And then I've got another square root. So right there, y equals square root x. There's my parent functions. Make sure you pay attention. If I tell you to do two functions on the same graph, one's the parent, I mean it, and I'm going to grade it accordingly. Now we're going to use transformations to graph the given function and answer this information about our transformed function. All right, so we've got our parent. We need to figure out what is this transformation. If you need to, reference your guided notes. But your pattern of transformations, let's see if I can get, here we go. Our pattern of transformations of functions looks like f of x equals, and then I have a coefficient out here, x minus h, whatever the function happens to be, plus k, where this is my vertical stretch if it is a whole number greater than 1. If it's less than 1, if it's a fraction, it's a shrink or compression. It's a fraction. This is my horizontal shift, left, right, and because it starts negative, it doesn't go the way you think it's going to go. This is my vertical shift, up, down, it goes the way you think. Horizontal is inside whatever the function is, squared, cubed, square root, absolute value. Horizontal is attached to the x. And then if I have negatives, negative out front reflects on the x-axis. Negative here reflects on the y-axis. Okay, so there's your pattern of transformations. You can keep that in mind. We'll put it there and see if we can do this. So we've got a negative out in front that reflects it across the x-axis. That means it flips it upside down. So a mirror image flipped upside down. My domain and range both have a limit. Now we're talking about the transformed function. My domain is 0 to positive infinity inclusive. My range for the original is 0 to positive infinity because it's up here, but my transformed is down here. So this range is from negative infinity up to 0 inclusive. These intervals always go least to greatest. My x and y intercept both at the origin, 0, 0. That's where it intercepts both the x and y axes. All right, let's look at our absolute value function here. What transformations do we have? Well, right here, this one starts out as minus, so it goes the opposite way we think. This goes to the left 1 and up 2 units. So this vertex is going to shift to the left 1 and up 2, so my vertex shifts over here. And then it's still a V shape. Opens about the same amount as the original. Vertex is at negative 1, 2. Now this graph goes forever left to right. My domain is all real numbers. My transformed function, the original, the parent, the range starts at 0, but my transformed function got shifted up 2. So the range for the transformed function is 2 to infinity. Now what about these intercepts? Well, it isn't ever down here on the x-axis, so there is no x-intercepts. You can say does not exist, DNE, or you can say none. Y-intercept happens where x is 0. So let's look at our equation. Y equals 0 plus 1 plus 2. 0 plus 1 is 1, absolute value is 1, plus 2 is 3. So where y is 0, x is 3. All right, let's look at the next two. Transformations of functions. We've got our parent function, y equals x squared. What happens with our transformations? What are we doing here? Well, this transformation moves me down 1 unit. This is a vertical stretch or shrink, guys. What do you think? Well, 2 is a whole number, so it is going to be a vertical stretch. So I take my vertex, I shift it down to -1. There's my new vertex. And when I compare my new parabola to my original parabola, what's happening to it? Think parabola. If this is my parent and I stretch it, grab the ends and stretch, it gets skinnier, right? So my new transformed quadratic function needs to be visibly skinnier than the original. Domain is still all real numbers. Once it starts all real numbers, it stays all real numbers, but my range is shifted down. Instead of starting at 0, now it starts at -1 and goes up to positive infinity. Y-intercept, well, that's where that vertex sits, at 0, -1. X-intercept, so this one's a little bit more work. To find the x-intercept, I set the y value equal to 0. So I take my equation, I say, okay, 0 equals 2x squared minus 1, and I solve for x. I add the 1 to move it over, and I'm trying to get that x by itself, so I need to divide out by 2. So that's just 1. I have 1/2 equals x squared. Well, to finish solving this, I need to take the square root of both sides. And anytime I solve by taking the square root, I do plus or minus because I don't know if my variable started out positive or negative. And that shows that I have 2 x-intercepts. That works. One is positive, one is negative. That also works. So my x-intercepts are square root 1/2, 0, and negative square root 1/2, 0. My 2 x-intercepts. Notice that I'm writing them as ordered pairs. My last transformation, let's see what we've got here. We've got a vertical stretch or shrink, and what kind of transformation is this one? It's underneath my square root, so it's part of what's going on with the function. It's attached to the x, that's my horizontal shift. It's still negative, that means I'm shifting it to the right because I plugged in a +1, shifted to the right one. And then what about this 1/3? 1/3 is a fraction, so it's going to be a shrink or a compression. So it is a compression or a shrink by a factor of 1/3. Well, what's going to happen if I compress or shrink my square root? I've got this curve here, and if I smush it like this, is it going to get curvier or is it going to flatten out? Well, the square root function flattens out when I compress it. So I need to move it to the right one. So I shift my vertex over 1 and I compress it so it flattens out. So that's going to be my transformed function. Domain and range. Domain and range both have limits. My domain for my original started at 0. I moved it 1. So now my domain starts at 1 and goes to positive infinity. My range, since I didn't move it up or down, my range still starts at 0. It's still going to positive infinity. It's just not going up as fast. Y-intercept. Well, this function is shifted away from the y-axis, does not open in that direction, so there is none. Or I can say does not exist. You don't have to say both. X-intercept is that vertex at 1, 0. All right. Excellent, excellent. Moving right along. Now we have some new stuff. Piecewise defined functions. Now, piecewise defined functions are kind of new, but not really, because none of the functions we're looking at are new functions. It's just we're not looking at the whole thing. It's like we're taking 2 different shapes, 2 different functions, and we're cutting them apart and putting them together. Okay, I'll show you what I mean. A piecewise defined function has different equations or rules that apply to different pieces of the domain. Did any of you ever have one of those books that had like, I had one that was like a Barbie, a fashion Barbie, and it had different sections, and it had, you could flip back and forth, so you could change your hat, you could change your shirt or skirt, or you had a monster and you could change out the head and the torso and the legs, I don't know, but different, so you cut it apart and switch back and forth. Well, that was moving vertically. This one, when we do piecewise functions, we're talking about moving horizontally, where we're going to take our domain and we're going to cut it. So like I may have half of a parabola and then I've got an absolute value or something like that. So let's go ahead and do a couple of these together. In fact, we're going to do that 3 of these together today. Graph each piecewise function using a different color to graph each piece. Remember to start and stop at the domain break, even if it's not included in that piece. So I go there even if it's not included. Well, for this first one, my domain break is at 1. 1 is right here, so that's my domain break. That means the left side of this function is going to go all the way to 1, and then the right side of the function is going to pick up here at 1 and move all the way to positive infinity. The left side of the function, let's do that first. Values less than or equal to 1. So for my x values less than or equal to 1, my rule is x plus 3. Okay, what is x plus 3? Well, that's a line with a positive slope. Okay, x values less than or equal to 1. So I'm gonna use 1, but that's going to be the biggest value I get. I get to include 1. If I plug in 1, 1 plus 3 is 4. That's my stopping place here, and it gets to be filled in. It gets to be included because it's included there. But I need, for a straight line, I need at least 2 points. So I need to pick another value for x that's in this piece of the domain, this left side. I could pick 0, I could pick -5, I could pick -200, but I need to pick something over here to show me where my line goes. I'm going to go ahead and do, let's do -4 and let's do 0. So where x is -4, -4 plus 3 is -1. Where x is 0, 0 plus 3 is 3. And then I go all the way to 1 and I stop there. I don't keep going because this is the piece of the domain I'm in. Let's go ahead and graph this line. So my line, I picked 1, 2, 3, 4, -4, and that is down here at -1. I picked 0. 0 is at 1, 2, 3, and then I picked 1. 1 gets included in this piece, and it's at 4. Now that's where I stop. There's an imaginary line here that I'm not going to cross with that piece of my function, okay? That's where my domain breaks. Let's draw that line. This line starts at -infinity and it goes up to where x is 1, and then that line stops because this line is just for this piece of the domain. All right, now let's look at the other piece of the domain right here. For x values greater than 1, my rule for my function is it's always going to be 4. Okay, well that's easy enough. X values greater than 1. 1 is not going to be filled in, but it is my jumping off point. So I've got to include it. It's an open circle. So I'm going to put a curve around this. This is my starting place. Now I need at least another value in this piece of the domain, anything bigger than 1. So anything over here, guys, on the right side. Let's do 5. Are we good with that? Because no matter what x is, what is y? Well, no matter what x is, y is going to be 4. So when I come over here and I say, okay, this has to be used because it's my starting place, but it's open circle at 1, 4 for this piece. But no matter how far over I go, 1, 2, 3, 4, 5, it's always going to have the y value 4 because this is my horizontal line. This is my constant function. So these two pieces, my domain splits at +1, 1 rule for one side, 1 rule for the other side. This line is not part of the graph. It was just to illustrate to you that that's where my domain breaks and the pieces of my function shift. All right? Okay. Oh my goodness. I see that my my piecewise function did not print. I'm going to have to fix that. Let me make a note to myself to fix that piecewise function. Okay. I will give you the piecewise function we're going to graph here. We are going to graph g of x such that, and we have two pieces. The first piece is going to be x plus 3 again for x values less than or equal to -2. And then my second piece is 1/4 x squared for x values greater than -2. So that's my piecewise defined function for this second graph. Write that in, pause me if you need to. We're going to go ahead and color code the same way so that we have the left side and the right side. This time my domain break is at -2. So this is where my function breaks at -2. So I have a left side, this first rule, and I have a right side, the second rule. So the first side, the left side of my domain break, x values less than or equal to -2, the rule is g of x equals x plus 3. Oh, that's that graph we just did. Exactly the graph we just did. So we know stuff about this, except we got to stop here this time. We can't go all the way to 1. We have to stop at -2. My break in my domain moved. It shifted back to the left. So I can't use 1. I'm going to go down. I'm going to use some values. My largest possible value in the domain for this piece is -2. It's included, so square braces. -2 plus 3 is 1. I need another piece of the domain. I can't use 0. I could use -4, and we already know that -4 is -1 because I've already used this rule before. So I've got -4, 1, 2, 3, 4, -1. I've got -2, 1, and this is included in this piece, so it's filled in. And there is this left-hand piece of my piecewise defined function. It's the domain goes from -infinity up to -2, and it stops. And then at -2, I switch rules. My rule for the other side of my domain break, x values greater than -2, my rule is going to be 1/4 x squared. Okay, this is not a straight line. What shape is this piece of my graph going to be? Well, it's going to be a parabola, and it's got this compression, this shrink of factor of 1/4, so it's going to be kind of a wide opening parabola. I don't include -2, but I gotta use it as my starting place. 0 is easy, right? For -2, 0, and then let's go ahead and pick another point. Let's do maybe 3. Ooh, 3 is going to be ugly. Let's do something even. What about, let's just do 2. Let's just do 2. Okay, so if I take -2 and I plug it in, -2 squared is 4. 1/4 of 4 is 1. 0 squared is 0. Anything times 0 is 0. That's my vertex at the origin. We were expecting that. And then 2 squared is 4. 1/4 times 4 is 1. Okay, this is the starting place, the jumping off point where x is -2. But it's not inclusive in this piece, so it's going to be an open circle. Now I want to point out to you that for both of these, where one piece stopped, the other started at the same y value. That is not always the case. Our next one is going to show you that. Okay, so this is my jumping off point. I go through the origin 0, 0, and then my parabola starts to curve back up. So I know what to expect because I know it's quadratic. I've got this parabola. It's going to curve back up forever. So we have one piece according to one rule, this linear rule, and we have another piece according to this quadratic rule. All right, one more example of a piecewise defined function. And I got this one printed off. That's good. So we have two rules again. The break in our domain is at 1. I want you guys to pause the video, see what you can do with this, and then come back. Again, you don't have to draw this in. This is just to emphasize to you, to remind you where to start and where to stop, so you don't draw one function too far. For x values less than or equal to 1, my rule is negative absolute value x. X values less than or equal to 1, let's do -3, 0. I got to go to 1. It's going to be included. The absolute value of -3 is 3 times the negative, -3. Absolute value of 0 is 0 times the negative, still 0. Absolute value of 1 is 1 times the negative is -1. So this is the piece I'm going to do on this left side. I've got -3, -3, 1, 2, 3, 1, 2, 3. Remember, an absolute value function is what shape? It's a V, right? And I haven't shifted this one, so the vertex is at the origin. It's just that it's been flipped upside down. This piece gets to be, this point gets to be included. So I've got this V right there, and then it stops because that's only this piece of the domain. The other piece of the domain has a different rule. For x values greater than 1, my rule is 2x. Well, what is 2x? What's that shape? Well, that's a function, that's a linear function with a positive slope, slope of 2. It's going to start at the x value 1, not included, and then it's going to go up. Let's just pick one more. Let's do maybe 3. Well, if I plug in 1 for x, I'm at 2. If I plug in 3, I'm at 6, and 2 points define a line, so we're good. This point 1, 2, where my domain breaks, is up here, not included, so it's an open circle. Then I'm at 1, 2, 3 up here at 6. So there is my line with a positive slope for this piece of my function. Excellent. Now, I want to point out to you that for all 3 of these piecewise defined functions, even though my domain split, everything was included. So even though my domain broke here, my domain is still all real numbers, because that piece, that point at x equals 1 is included. My range here would be -infinity up to, what is that? 1, 2, 3, 4. 1, 2, 3, 4. My range would be -infinity up to and including 4. For this one, I've got a split at -2, but it's included, so my domain is all real numbers. My range is also all real numbers. For this graph that we're doing now, though, my domain, all real numbers, nothing is left out, but my range has a gap. This range goes up to 0, and then the function does not happen until I get up here to 2. So my range would be from -infinity up to 0, inclusive, because that point's filled in, or it picks back up at 2, but 2 is open. So starting at 2 but not including, all the way to positive infinity. That would be domain and range for this function. Alright, this video is as long as I wanted it to be, so we are going to not do this application problem together. I want to encourage you to have a go at it, kind of think through it, sketch out some things, and we will work on that in class together.